even though Desmos does not work with recurrence relations, we are going to spend some more time with them. So we have a recurrence relation generated here and down below for these two examples. We want to write the first four terms of the sequence and make a conjecture about the limit of that sequence as n goes to infinity. Sorry, that ended up over here and I'm not sure why, so I put it over here to make more sense. Okay, so, well, we have the first term given to us. We know that C1 is equal to 25. Now C2, for C2, n plus 1, so n plus 1 is 2, we would take the last one, C1, and subtract 5. So that means that this would be 20. Right? You take your last term, subtract 5. C3 would be the last term, C2, subtract 5, so that would be 15. And C4 would be 10. Now we're starting at 1, by the way, because it tells us right up here in this bit right here, even though I'm working with C sub n, not A sub n, but you can see down below in particular that it tells us it wants us to start at 1. See that little bit right there? So we're starting at n equals 1 as the start. So that means that right here, right, n equals 1 is our start. Otherwise, technically, we could find C sub 0, right? C sub 0 is pretty obvious, but it's in there and we could find it. All right, so I made the first four terms. Where do I think this is going? So what do I think is the limit as n goes to infinity? Let me just do this in a different color, just to try to keep it clear, because that was part A, right? Part A is come up with the first four terms, so we did that right here. Part B is where do you think this is going to? Where do you think you're going? So part B is the limit as n goes to infinity as C sub n. Sorry, that wasn't different enough. Let me try green. Oh, that's better. All right, so then it's asking make a conjecture. So what do we think is happening as n goes to infinity of the sequence C sub n? Put it in braces, of course, those little curly braces to show that it's a sequence. Well, I think this is going to keep going down and down and down and down and down forever. So I think it's going to head towards negative infinity. So that's the answer to the second question they asked, and this is the answer to the first question that they asked. All right, now what about this one? D sub 1 is 1. D sub 2 would be 2 times D sub 1 plus 3, which would be 5. D sub 3 would be 2 times 5 plus 3, which would be 13. D sub 4 would be 2 times 13 plus 3, which would be 29. All right, so there's the answer to part A right there. Where do I think this is going? I think it's going to infinity. That's where I think it's going, right? So the limit as b goes to, oh no, sorry, as n goes to infinity of d sub n. You have to put it in the curly braces in order to notate that it's a sequence, is infinity. Which for the record means that I think that those sequences are divergent. We'll talk about that more a little bit later. But because these are both heading towards infinity, we think this is a divergent sequence. Same with this one. Right, if it heads either to infinity or negative infinity, that is a divergent sequence. We'll get those definitions in a couple pages, but I think it's pretty obvious at that point. If you're heading to infinity, you're going nowhere good. All right. So then let's work with sequences just a little bit more so we can kind of develop a couple definitions. And then we're actually going to double back to that example really quickly. All right, so I have a relation here. Let's see. I want to find a recurrence relation that generates the sequence using, both the natural numbers and the whole numbers. Sneaky. So I'm going to show you what happens if you decide to start at 0 versus you decide to start at 1. And we're going to develop the next two terms of the sequence, write a recurrence relation, and write an explicit formula. Oh my goodness. So we have all sorts of work. Okay. So let's start with this first one. Let me just kind of put in a table over here. Okay, so if we look at our a sub n values, it's 7, 10, 13, 16. Looks familiar, right? Because we've already seen this. So the next answers, the next two terms would be 19 and 22. So if you like, there's your answer for part 1, right? But I can put it over here. So part 1, 19 and 22 are the next two numbers. Done with that, right? Actually, let me label them, because otherwise it's just two numbers just sitting there, and if you're going to go back to this page and wonder what you were doing. There we go. Now, we need to define this recurrence relation twice. We're going to do it as a natural numbers, and we're going to do it as a whole numbers. So let's start with the natural numbers. So natural numbers will be n is equal to 1, 2, 3, 4, 5, 6. So I want a relation, and it's a recurrence relation. So for part 2, I'm looking for a recurrence relation. That's using this sequence, right? So how do I start it? I say, well, a sub 1 is 7. A sub 2, or a sub n plus 1, the next one, is the last one, plus 3. We've already seen this relation. Done. That wasn't hard. So those are the natural numbers. Natural. Now, how will this change if I use the whole numbers instead? Well, then that means we start at 0. Well, that's not going to affect the... I'm going to do this really quickly just to kind of segment that off for our own benefit. All right, so that's not really going to affect the relation because I'm still adding on 3, but it is going to affect my starting point, right? So my starting point would be with the whole numbers. A sub 0 is 7. A sub n plus 1 is still a sub n plus 3. It just changes what index you're starting at. So we start at 1 or we start at 0. All right, so there's the recurrence relation piece, and that was actually pretty easy. Right? The recurrence relation does not change very much. What does change a bit will be my explicit formula. And again, it's going to be a small tweak, but it's an important one. I can see that I'm adding on 3 every time, right? So I got that bit. Now, if I'm going to make this into a relationship, though, just forget about the whole numbers for a second, and you want to come up with a mathematical relationship between 1 and 7, 2 and 10, 3 and 13, and so on. Then those natural numbers, remember, it's just one formula, would be a sub n, and you're making it into a function. Well, that's linear, right? It's going up like a straight line. So to be 3, because that's your slope, 3n. Well, 3 times 2 is 8, right? Oh, no, 3 times 2 is 6, excuse me. 3 times 3 is 9. 3 times 4 is 12. So I'm off by 4 every time, right? 3 times 1 is 3. So 3 times 1 is 3. So if I add 4, that'd work. 3 times 1 is 3. 3 plus 4 is 7. 3 times 2 is 6. 6 plus 4 is 10. 3 times 3 is 9, right? That'll work. The whole numbers, a sub n is, now forget about the orange one for a second and just kind of look from the green. I'm going to be adding 7, right? Because I have to get from 0 to 7. So it's going to be 3 times n plus 7, right? Because 3 times 1 is 3. 3 plus 7 is 10. 3 times 2 is 6. 6 plus 7 is 13. 3 times 3 is 9. 9 plus 7 is 16, and so on. And you can see there's a relationship here. You shifted the graph, And so you end up shifting it down by 3 because 3 is the slope. So instead of 4, it's at 7, which is 3 larger than 4. That's because this particular sequence, it has this very special pattern, which I want to talk about right down here. We're going to skip over the example in the middle for just a second. What we're seeing here is an arithmetic sequence. An arithmetic sequence works in very particular ways. So it goes from one term to the next term by always adding or subtracting, because subtraction is just adding with negatives, right? The same value d. Note that d would be the slope, right? Slope. Oh, let me do it in blue here. The slope of a linear explicit formula. So see example A. Right? So for us, that D is 3. See it right there? So D is 3. It's the slope. Slope of that explicit formula. And this is linear because, of course, we're adding on the same amount every time. So that is an arithmetic sequence. So part A is an arithmetic sequence. Part B will be geometric. So this one is arithmetic. Now, part B, not so arithmetic. So the next two terms, 8 times 2 is 16, times 2 is 32, times 2 is 64. So the next two terms for part 1 would be 128 and 256. Okay. Now, if we want to make this table again, just to kind of help ourselves, because we know, it's useful. It's not strictly necessary. You can do it all in your head. But since this is our first time, we'll try to figure this out. So this would be 8, 16, 32, 64, 128, 256. Okay, if I'm doing the natural numbers, this would be 1, 2, 3, 4, 5, and 6. Okay, so for a recurrence relation, which I'm going to do over here, for the natural numbers, I would say a sub 1 is 8. Oh, sorry, b sub 1. I switched this letter, right? So we do that all the time. We'll just change it to different letters. So b sub 1 is 8. Sorry. And b sub n plus 1 is equal to 2 times b sub n. I mean, the recurrence relation ones on these are super easy. You just take the next number and multiply. Right? To get that next number, you multiply by 2. Multiply by 2. Multiply by 2. Easy peasy. All right, what about the whole numbers? The whole numbers would start at 0. Well, it's not going to change the multiplying by 2 piece. It just changes where you start. So you say b sub 0 is 8. And then b sub n plus 1 is 2 times b sub n. It's basically the same relation, but with a different starter. Recurrence relation's easy peasy. Now, what's going to be more fun is the more useful explicit formula. Okay. So for the natural numbers, I need to come up with a way to define b sub n as a function of n that will always work. Okay. Well, there's actually several ways you can do this. There's a few of them, but you'll notice that we're always multiplying by 2. There's a ratio in there that we're multiplying by. Okay, so it's 2 to the n times 4. I mean, double check me. And these are the ones that it's kind of like magic. You just have to figure them out. So you need a relationship that will always work. 4 times 2 to the 1 is 4 times 2, which is 8. 4 times 2 to the 2 is 4 times 4, which is 16. 4 times 2 to the 3 would be 4 times 8, which is 32. 4 times 2 to the 4 is 4 times 16, which is 64. It works. But there are more ways. 4 is really 2 to the 2. So, I mean, there's so many ways to do this. You could say b sub n is 2 to the 2n plus 2, because that's 2 to the 2. 2 to the 2 times 2 to the n makes 2 to the, oh, that's right, that's n plus 2. I'm sorry. I got too many 2's in there. That would work also, right? There's a lot of ways to do these. It's also 8 times 2 to the n minus 1, right? There's tons and tons and tons of them. Either one of these will work. And there's more. All right, now what about the whole numbers? Well, it's going to have that same relationship, right? So for the whole numbers, I need it to work when I put 0 in. This is 2 to the 3rd. So b sub n would be 2, well, how about this? 8 times 2 to the n, right? Because 8 times 2 to the 0 would be 8. 8 times 2 to the 1 would be 16. 8 times 2 to the 3. That would work. Or you could do what we did here. B sub n is 2 to the n plus 3, right? Because 8 is 2 to the 3rd. Either one of those would work. And in case you missed it, these are not arithmetic. We're not adding on the same amount every time. No, 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 no. We're multiplying. So that is called a geometric sequence. A geometric sequence is when you are multiplying by the same constant, and that constant is called the ratio. In our case, it was 2. So it's this number 2 right here, 2 right here, 2 right here. 2 is our ratio, and right here, right there. That r is the base of an exponential explicit formula. See how these are all 2 to a power? So it's the base of an exponential explicit formula. See example B above. So this is geometric. R is equal to 2 on this one. Actually, I could have mentioned that up above. So this one was arithmetic with that difference being 3. Right? D was equal to 3 on this one. This one's geometric with R equal to 2. And you can see the 2 is right here, the 2 is right here, the 2 is right here. That base for every one of your explicit formulas, because all your explicit formulas will be exponential. Doubling back to the previous example, just like I promised I would, you can see that this particular one, we didn't ask it at the time, it's arithmetic. And you can see that your difference is -5. You're subtracting 5 as you move down, which means that a sub n is equal to -5n plus 25. Right, from n equals 1. Oh no, it's plus 30. Right, because if I put 30 here, when I put 1 in, I'll get 25. Right, so 30, because this must be c sub 0 right here. And that will be that relationship, because I want, when I substitute 1 in, for it to work. And it will if I make that 30. All right, so obviously these two types of sequences are going to be important to us. They're going to lead to other things. So arithmetics add the same amount every time or subtract it. It's called the D for difference. And that is the slope of a linear explicit formula. As opposed to ones where you're multiplying by the same amount every time. Also, it could be division. And that would be the ratio, which would be the base of an exponential explicit formula for that sequence.